Thank you for the introduction. My name is Agnisham and I am a scientific programmer in the ERATO group. So today I will be talking about verified regular expression matching. And this is work that I did during my PhD with my advisor, Dr. Mamuras, and my friend Angela. So we have all used regular expressions in our favorite text editors or with grep, but regular expressions are also used in many other domains. For example, in the domain of security, to detect network intrusion detection, people often use regular expressions. For example, Snort is this community maintained database with 5,000 plus regular expressions, perhaps even more, which are used to detect intrusions in networks. And antivirus tools like ClamAV, they have these regular expression signatures which are used to detect malware. And regular expressions also appear in domains like bioinformatics, for example, to describe sequences of proteins. One such database of protein motif sequences is ProCite. So how are regular expressions matched in practice? So we start with some regular expression like this. And one option is to turn it into a backtracking based parser. And the other, so this kind of parsers are very popular, but they can be quite slow on exponent on the worst case input. For example, if you have this string and this kind of regular expressions, the backtracking parser has to try all possible paths along the in the parsing program to see which one matches. The but these kind of parsers are very popular. In fact, the regex libraries that are bundled with most programming languages have this kind of regex matchers bundled with them. The other option is to convert the regex into a finite state machine. And with this, we can do linear time matching of these regular expressions. And these are available in some tools like RE2 developed by Google and Hyperscan developed by Intel. And the drawback with these things, however, is that they tend to be less flexible. And what I mean by that is when there are additional features which are not there in classic textbook style regular expressions like back references or lookarounds, then people tend to implement them more easily in backtracking based parsers rather than finite state machine based parsers. The parsers that the regular expression matching engines that we are going to uh, look at today are mostly going to be of these finite state machine kind, and we will hope to get linear time matching. And another aspect of this talk is about verification by theorem proving. So what do I mean by this? When I say verification by theorem proving, the first step here is to have some kind of specification in a formal language. So in this example, I'm talking about sorting, and what I would want to do is I would want to write down in some formal language, in this case, Coq, what I mean by sorting. And then I would give an implementation. And usually this implementation is some kind of functional algorithm. And then I would state the theorem saying that the implementation satisfies the specification, and then I would supply a proof. And with the help of a proof assistant, this is done in an interactive manner. So the user interacts with the proof assistant using tactics. And these tactics are things like applying induction or applying a previously proven theorem. And then the proof assistant says whether this step is a legal step in the uh, logical framework or not. And in particular, much of the work that we did in that I'm going to present in this talk, it was done in the theorem prover Coq. So this framework makes a very reliable style of proofs because ultimately the proof checking relies on a very small logical core. But this also means that doing this is very challenging because the proofs have to be spelled out in all the gory details. And in normal proofs, we rely on human intuition, such as drawing a diagram, or when we realize that certain kind of patterns emerge in the proofs, we are able to understand how to simplify them or generalize parts of these proofs. But this style of reasoning is not available most of the time in a theorem prover. And this means that practical projects can be very large. One very well-known project that was carried out in this domain is the CompCert compiler. This is an optimizing C compiler, about which various correctness theorems are proven. And it turns out that this project took 100,000 lines of code and 6 person years. So this talk is going to be about the formal verification of algorithms for regular expression matching. And I'm going to discuss different avenues for doing so. But before I do so, I want to discuss a kind of rubric with which we can evaluate how good each of these techniques are. So the first thing we will want to look at is, when we look at an algorithm, we will want to know how efficient the algorithm is. The next thing is, when we have certain mathematical objects that will arise in the proofs, or when we reason about the algorithm, we want to know if they're elegant. This is obviously subjective, but it is kind of nice to look at. And we also have to know how tedious are the proofs, because as we discussed before, it is important to have proofs that we can carry out with reasonable effectiveness. And part of this is, I also want to know if I can represent these algorithms purely functionally, partly because it's elegant, and also partly because these proof assistant languages generally tend to be functional languages. And when we have a more functional style algorithm, it's easier to reason about this in this kind of system. So the first part of this talk is going to be about the very traditional technique of formalizing, of converting regular expression into Thompson style NFAs. And we have all seen this in an introductory automata theory class. So um, we have the empty expression, and then we have characters. And then when we have concatenation, we create the two automata, and then we glue them at the middle. And then we have the choice or union, and then we have Kleene star. So one thing to note here is that when we do this construction, we make sure that the out degree of every state is at most 2. And then the other thing I notice here is that I am using epsilon ages. So these are choices that I am making, and I could have done otherwise. This is not mandatory, but we will see how this impacts the formalization effort in the next few minutes. So how do we prove the correctness of this sort of construction? We prove things about the paths in the automata. And when we have runs in the automaton for the concatenation, we have to say that this run can be decomposed into a run in the automaton for R and the automaton for S. Or similarly, if we have a run in the automaton for R plus S, then it's either a run in automaton for R or the automaton for S. And similarly, if we have a run for our Kleene star, then we can decompose this into many runs. And this means we need to reason about these paths and graphs. And we have to develop this framework for representing these paths. So the first question is, how do we represent these graphs? And for our formalization, the avenue that we chose was to represent the vertices with natural numbers. And the graphs were functions which assigned a successor to each vertex. And This means the successor was a enumerated data type containing, like, saying either there are no successors or one successor, or it's a choice node with two successors. And then the paths were either list of edges or list of vertices. And it was not clear to me which one is a better choice. And in fact, I was doing this work with another person who was using a different definition from me. So we had to write some glue code translating my lemmas about paths of edges to paths of lists of vertices. So it is quite difficult to come up with a very canonical definition for these sort of things because we have lots of choices here. Another thing to note is that I did very little usage of dependent types. So for example, what I mean by this is that I just used natural numbers for vertices, but someone might want to use finite type, saying that these vertices all satisfy some predicate that they are less than some natural number. And similarly, like for the paths, I might want my definition of a path to include the idea that this age, if I have two consecutive edges, then the target of the first one is the source of the next one. So we have to have like lots of these sort of predicates to define the concept of path. And instead of uh, putting these putting these facts in the type itself, I wrote this external predicates saying that these are the things that my path satisfy. So when I was reasoning about a path, like this information was conveyed with the help of an external predicate rather than being packaged into the type itself. And one of the reasons is that with COG, like their tactics have pretty limited support for dependent types, in my opinion. Uh, be- but with having this kind of external predicates, uh, it seemed more manageable. There are some people have looked at somewhat similar formalization efforts. So this paper from Tobias Nipko, he used a list of bits approach to represent the vertices. And this means that when there was some operation like concatenation or union, he padded an extra bit saying which of the two components of the concatenation or the union that vertex belongs to. A similar approach I have seen is by Dochkal et al. From CPP 2013. And this is a very similar idea, except that instead of using a list of bits, which is somewhat more primitive, he used sums and products of finite type. So sums for unions and then products for concatenation, showing which of the two components the vertices belong to when you make one graph from the two smaller graphs. Um, one of the so I feel that with this approach, sometimes the proofs can be shorter, but they are also sometimes somewhat hard to understand. And one thing to note here is that with this approach of uh, having just one integer to represent the vertex, we could probably get a better runtime representation. But maybe this was not a consideration for their approach. And so for these definitions and lemmas related to paths, we had to write around 3,000 lines of code. And this involved lemmas about like gluing paths together and what accepting runs are and observing the strings that are on the paths and so on. And similarly, so we had to do something similar about when reasoning on paths. And so one of the features or one of the choices that we made was to simulate NFAs directly rather than going through a step of determinizing first and then simulating the deterministic automata. And here what we do is we maintain what I will call the set of active states. And the set of active states are these states which for which you have a path on the current word from the initial state to that particular state. And we noticed earlier that our automata may have epsilon transitions, which means that we might have these loops which are unproductive. That is to say that on the prefix that we have consumed, we might be able to find multiple paths if we allow loops. So we need to carefully do a careful exploration, keeping track of which states we have already visited. We would want to do something like depth first search or some basic graph search algorithm, but this is not as simple as simply taking the successor until we have this is we have to keep careful track of such kind of things. And we also noted that each state has at most 2 outgoing edges, and this helps us to understand how much work we are doing for exploring the graph. And the graph, this means that the graph has OM many edges, and this means that we would be doing OM work per new character. So M is the size of the regular expression that we started with. And another thing we could have done here is to go with an epsilon free automata. So instead of Thompson construction, we could have done something like Glushkov construction. And this would give us another kind of NFA, which would not have epsilon edges. But it turns out that there would be some. So if we do this naively, we might get quadratically many edges in the graph, quadratic in the size of the regular expression. And it turns out that in fact, if you want linear number of edges, you have to have epsilon free. You have to have NFA with epsilon edges. And there is a pretty old paper showing why this is the case. So we have, as a part of exploring the Thompson NFA, we have some kind of graph search. We went with DFS. So one of the things I want to note here is that we have a fuel parameter. So all the functions in Coq are required to be total. And here we have this. Here we have this graph exploration, and based on the definition of the type of the graph itself, we wouldn't know that this terminates. So we supply this additional fuel parameter, which is like a recursion depth, and this is the simplest way to make this go through the termination checker. Other way would be to add like some kind of proof saying that the number of unvisited nodes are decreasing. But this is probably the simplest approach, and this works. And then the other thing I want to note here is that I am using sets. These sets are keeping track of which vertices have already been visited. And this also brings in a can of worms, because we have the question of how shall we represent these set values. So I will come back to this, but the other question is, how do we prove the correctness of the DFS algorithm? And the main answer to this question is to know this. So for answering this question, we need an auxiliary definition, which is uh, which is shown in the slide with this predicate r s comma x. So S stands for source and X is for do not touch. So this is the set of vertices reachable from S which do not touch X. And once we have this definition, we are ready to show the invariant for DFS. So the DFS uh, gives us this, uh, computes this. In particular, it computes all the vertices from a given set U, which do not touch X. So there are certain key steps we had to, like, these are some lemmas we had to prove for the correctness of DFS. And I will just summarize them briefly. So one of the observations is the following, that if we have, if the source is uh, consists of S1 and S2, then when we can first search for the vertices that are reachable from S1, and then when we start to look for the vertices reachable from S2, we can ignore the vertices that we have already explored. And this is the key idea behind how DFS operates, mainly to uh, we are always allowed to ignore the states that are already visited, and this uh, idea can be encapsulated with this particular equation. And so the main thing we want to do with DFS is uh, compute the closure, and by this I mean that when we have reached some uh, set of states, we want to know what are uh, what are the set of states that are reachable from my current set of states without consuming new letters. And we can do this by doing DFS repeatedly. So we have this finitely many states that we currently have, and then to compute the closure of this, we can apply DFS repeatedly. And this takes about 2000 lines of code to prove. So actually not that much compared to the definition of paths, which were supposed to be elementary. But the other thing is sets. So we have to maintain this set of visited states. And generally this is done using keeping a mutable array of booleans. And we just change this array to, we keep a 0 to say that the state has not been visited, and a 1 to say that the state has been visited. But generally, this is a mutable array, and proof assistants, including Coq, are usually functional. So if we do this, so the way we went about this was that inside Coq we had an axiomatized representation of arrays. This means that I wrote certain equations saying that I have a data type called array, and when I look at it through certain functions or I do certain updates, they behave like this. But uh, inside Coq, it's opaque in the sense that I can only reason about it through these equations. And this is what I mean by an axiomatized representation. And when I extract this, so perhaps I have skipped this, and I should explain this. So I have a step, like once I have this verified uh, code in Coq, it is possible to extract it into OCaml or Haskell code, and then you can not look at the Coq type checker at all, and you can just run this OCaml or Coq, OCaml or Haskell code, and this is a great way to get programs which are verified. So coming back to our implementation of sets, we slightly cheated here. So we have this unfaithful extraction, and here we have a function set, which according to Coq, it's a pure function. And but when we extract this to OCaml, we extract this to a method which mutates the array in place. However, and our algorithm, namely depth first search, this always uses the array in a linear manner, in the sense that when I do this, I do not use the older copy of the array, and I just use the newer copy of the array. So it is fine to mutate this in place, but this is uh, a part of the extraction, like part of the extraction, which is unfaithful to how the code works in Coq. And this part of this is unverified, and in principle, I could have made a mistake over here, which uh, is unverified. I will discuss some other approaches which we could take. So one approach is to use a purely functional alternative for sets. And these are based on some kind of binary trees. And if you do this, instead of a constant time lookup or a constant time mutation, you would have a log n time mutation or a lookup. So in here is the size of the array. So this is one option. The other option would have been to wrap it in some kind of a state monad. And when this is done, this would guarantee the linear usage of the array, but this would make the code look more complex. Another interesting thing, relatively recent, is I don't have a lot of experience with this, but I have seen this mentioned in a few places, is the functional but in place paradigm. So apparently this is implemented in Lean, and this is a very special optimization in Lean, which allows the Lean compiler to inspect the program, and the Lean compiler would look at the program and realize that some variables are indeed being used linearly, and the Lean compiler would uh, smartly do the mutation itself by itself. So this optimization would be done by the Lean compiler rather than yourself. So your hands are clean. But we went with the most unfunctional approach, perhaps. So just to recap this part of the talk, the efficiency over here, we built this linear sized NFA from uh, the regular expression. And we also know that this has linearly many transitions, because we know that there are at most 2 outgoing transitions per edge. And then we explore this automaton with a depth first search by uh, doing again as much work as the number of transitions potentially in the automaton per character. So let us look at this rubric and try to understand how good this approach is. So this is quite subjective, but I will talk about it anyway. So I think this is a very classic algorithm. So actually, maybe it should have been 5 stars here. And proofs, I found these proofs quite tedious. And this is also extremely efficient, because my approach aside, like you could have very compact representation of the automaton and like very efficiently do all of these things which I'm doing. And functional maybe, but we have quite a few hiccups on the way. So maybe not so much functional. The next thing we are going to look at, next we are going to talk about derivatives. And this is quite, as we will see towards the end of this part, like this is quite popular among in the formal verification community, because the semantics of these objects are quite elegant. And so I will introduce the concept of derivatives, which many of us probably already know. So I have this word word U, and I have a language L. So U inverse L is all such V, such that UV is a word in the language. And observe that if I have such a if I can check if U inverse L has the empty word in it, then I know that U is in L by definition. So, and then if U is A1, A2 up to AN, then I can, and there is some way to compute the derivative letter by letter. So, well, compute these inverses letter by letter, then this is a way for me to define the um, derivative by U. And also we know from some automata theory that if L is regular, so is this particular object. And so now we will talk about derivatives. So what we are going to do is that we are going to define this map, which gives me a way to compute this object A inverse R in the form of another regex. And in the previous slide, we saw that if we can do this, then we can apply this thing one by one for the letter that for the word that we care about. And then this will give us a way to do regular expression matching. So our goal is to define this this map delta or backslash partial, and then we will have this other map new which checks if some regular expression is contains the empty string. And so if we do this by what we saw in the previous slide, we can repeatedly apply del a few times, and then we can use new to check if there is the empty string, and this will give us a way to check if something has been accepted by something is in the language of the regular expression. And now we have not introduced any other concepts, like all we are dealing with is regular expressions and language. We don't have to have a concept of an automaton. And so this concept is widely attributed to Brozovsky, and Brozovsky showed that these gave some equations to compute these things. And here we have this function new. And as we discussed in the previous slide, new checks if the empty string is in a given language. So if we have concatenation, then the empty string is in the concatenation if it is in both the left part and the right part. Similarly, if it's in the union, if it is either in the left part or in the right part. And then there is also a very straightforward definition for the del function, which actually computes these derivatives. So here we have concatenation, which has some casework. So when we look at the derivative of R concat S with respect to A, then we need to know if if the empty string is a member of R. If this is not the case, then we can write the derivative in this manner. Otherwise, otherwise it is possible that some of the words in the derivative, that is A inverse R concat S, they might come from derivatives of S itself. So we have two different cases over here. And this is interesting because when we write derivatives in this manner, we might double the size of the regular expression, because here on the left hand side I had S once, and on the left hand side I have S twice. And similarly for R, this is a straightforward way to write the derivative of R. Basically, we have any derivative of R followed by multiple or any number of copies of words from R star itself. And here is an example of something which might actually, which does indeed actually cause the derivative itself to physically double. So here we started with this expression, which is uh, kind of pathological, but if we do compute these rules, we see that this expression indeed occurs twice in the result. So the question is, if we do this like with we get multiple characters in the input, and then excuse me, when we do this, the size of the derivatives, they can grow exponentially. Here it's exponential in terms of the length of the input, not the regular expression itself. And then the main question over here is how can we control the size of the derivatives? And in the original paper, Brozovsky considered these axioms. So the axioms are associativity, commutativity, and idempotence with respect to union. And what Brozovsky observed is that when you quotient with respect to these three axioms, you get finitely many classes. So I'm not sure if so. There are exponentially many such classes, which is expected because in some sense these derivatives that we are computing, they uh, let you form a DFA, so it is kind of expected for this to be exponential. But Brozovsky was primarily concerned with like showing that this DFA can be uh, computed, and there are indeed like finitely many such classes. And then we know that there are these many possible classes, which is unavoidable. But then the other question is how big are these expressions? And I don't know the answer. This is quite unclear to me. And also, there are certain axioms, like certain relatively simple axioms that are missing from the ACI simplification rules, which might allow you to make the which are relatively simple to implement, but they might allow you to keep the derivative size small. But we do not have great theoretical results on this. So there are other notions of derivatives which people have looked at, and some of them keep the size small, and uh, they maybe they would be a good candidate for formalization, especially if we want uh, our algorithm to be efficient as well. So there is this notion of canonical derivatives. So here, uh, these derivatives are uh, defined with respect to a set of letters, and this definition might require you to linearize the regular expressions, meaning that when you have something like this, you have a plus b a star, you want to look at the first a as one character and the second a as a different character. And later, uh, Gruber and Holzer proved that with certain kind of simplifications, you can always keep these canonical derivatives at most quadratic in size. And another notion of derivatives we see in the literature are partial derivatives. And with partial derivatives, the idea is to not just have one derivative, but a set of derivatives. So if Brozovsky derivatives are a way to represent represent DFAs in the sense that the derivative shows us which DFA state we are at. Partial derivatives are a way to look at regular expressions as if they were NFAs, because we need to have multiple active states rather than one single active state at a time. And these were introduced by Antimirov. And here you have a list of, or a set of derivatives for a given word. And instead, and what the interpretation of this is that uh, the derivative of R with respect to W, if you have this set, then the union of this set is supposed to give you the actual normal derivative. And since these partial derivatives would actually be a sub-expression of the original expression. So in this case, we do know for a fact that uh, the partial derivatives are each bounded in size by a linear bound. Derivatives are extremely popular in the formal verification community these days, and also have been for a while. So Brozovsky derivatives have been formalized. Well, maybe to here I say 2011, but this is also an exercise in software foundation. So maybe it was done even before that. And Antimirov derivatives have been also formalized. So regular expressions with lookarounds. So these are regular expressions which have certain kind of additional predicates, saying that when you look ahead beyond, like when you look to the rest of the string without matching it, you assert something about this. These are expressed with the question mark equals operator in PCRE syntax, if you know about them. So recently this has received some attention, and people have solved this problem using derivatives. So there is POSIX style lexing. What I mean by this is POSIX style lexing means that when you have a word and you want to find the leftmost longest match, that is what POSIX style matching implies, along with some additional rules which I am not explaining. But this problem also has been solved using derivatives. So some people have looked at something which they call symbolic Boolean derivatives, and this is now integrated into Z3. So Z3 is an SMT solver, and one of the theories it has, perhaps it's rather new, is the theory of regular languages. So you could throw into Z3 like some logical expression involving regular expressions, and you could ask, is this language empty, or and questions like this. And it so currently the way it solves these kind of questions is using derivatives. Derivatives also have been used for temporal logic monitoring. So this is from 2003. So yeah. So let us summarize this part of the talk. So elegance, I think it's extremely clean. Proofs are also very easy because it's supposed to be like one of the exercises in one of the chapters of software foundation. So great. Efficiency, it's kind of unclear because of the reasons we discussed. The very basic implementation is quite inefficient, but given that many authors are claiming that in practice you can add a lot of relatively simple simplification techniques to make it somewhat efficient, but it's kind of unclear what the theoretical guarantees on that are. And is it functional? I would say definitely. So I am going to proceed to the next part of the talk, which is what I call marked regular expressions. And this here I have the data structure for marked regular expressions. And basically, these are exactly like regular expressions with one new additional thing, which are called marks. So here we have a mark on A, and here we don't have a mark on A. And if you are interested in this, you could read this very well written functional Perl called a play on regular expressions. So fun fact, I was looking at the website of this author, and it turns out like about 10 or 12 years ago, he was also visiting NII. And uh, one of my papers, which is going to be presented in CPP next year. So this is also about the lookarounds problem, but I do not use derivatives. I use this technique instead. Is this one also uses this marked regular expression approach. So what are these marked regular expressions? One way to think of this is that these are just like NFAs, but they are inductively defined. So instead of thinking of them as graphs, which could have any arbitrary structure, we will think of them as very specific kind of graphs where we have concatenation nodes or union nodes or Kleene star nodes. So for example, this is my um, this is my regular expression, and I could look at this as an abstract syntax tree. And here I am going to think of this as some kind of an NFA. And I have not drawn the implicit NFA structure, but let's say that we have the input prefix A. And when we get this input prefix A, my active state would be A. And I am placing a token over here on A. And I am denoting this fact with this mark on A, showing that there is a token over here. So now let's say that I have this input expression AB. So now I am putting a mark on here and here. And these are, if I drew an NFA, these would be the possible places where I could have had tokens. And I have like these two tokens over here. And this is being represented by in the marked expression by putting these marks on this B and that B. And then let's say I have this expression ABB, so I got another B. And now this B could end up in, like, depending on the path that I take through the NFA, I could either end up here or here or here. And this are the three possibilities. So this is why I mark each of the three Bs. And this is the main idea of this is the main picture I have in mind when I think of marked regular expressions. They are just NFAs, and in the data structure itself, I have an additional mechanism which lets me represent where the tokens are. So let's consider this snapshot from the last slide. And this is something I will call a final mark, because if I did think of this as an NFA, and I'm going to make this more formal a little bit later, this would actually be a final state in that NFA. And this token indeed says that there is a token in the final state. And these are marks, but these are not final marks because they do not correspond to tokens in any of the final states. And now I'm going to define these simple functions. They are simple because they can be like written in terms of pretty simple equations. And the first one, so these functions are how I will reason about my marked regular expressions. The first one that I'm going to talk about is this function f. So if checks if my regular expression has any final marks. So most of this is quite simple. So if I have the empty string or an unmarked character, then I have no final marks at all. If I just have the character with a mark, then that is indeed fine. That indeed has a final mark. If it's union, I look into both of the branches. For star, I look inside. I look inside the final character of the automaton that is under the star. And the case for concatenation is the most interesting, as it's going to be for the most of this description. So here if I do have a mark on S, which is a final mark, then indeed it's a final mark for the whole thing. Otherwise, let us say that we are in the case where R allows empty strings, and we can check this by using this function new from the previous part of the talk. And so if this is possible, then if it is possible for R to accept empty strings, then if we have a final mark on S, then that would be a final mark for our concat S.
Some typo here.
There is some typo here. It's supposed to be, yeah. It's supposed to be new of S and F of R. My bad. And okay. So the next thing I'm going to do is I'm going to see how I can put initial marks here. So if this was an NFA, this would be my initial states. So, excuse me. So this A would be an initial state. This B would be an initial state, and so would this B. So I would put tokens over there, indicating that these are possibly initial states, or these are initial states. And so this B is an initial state because I could ignore this star by doing 0 iterations of it, and then I could just start my matching from here. By doing this, I could say that this is an initial state, and if I do choose to do this star, I could either go here or go here. And I define this function iota, which will put initial marks on each of, which will create a marked expression so that we have initial marks on the supposedly initial positions. And here, I hope there are no typos this time. So here with epsilon, I'm not putting any marks because I cannot. And if it's a single letter, I just put a mark. And with union, it's simple. We mark the initial places in both. With star, we mark the initial places under the star. And here is the case for concatenation. So if R allowed the empty string, then we would have to mark the initial positions in S and the initial positions in R. If it didn't allow any empty string, then we can only mark the initial positions in R. The next part is shifting marks. And what I mean by that is doing something like this. So for this B, these are the possible next states as shown by these dotted arrows. So when I do this shift operation, I put tokens which are supposedly this on this supposedly next states. And this is what the shift operation is supposed to do. So, and I can define this shift operation as well using very similar techniques. So the empty string and the marked or unmarked characters are quite simple. So is the union case. So here we look at the concatenation case. And when we have, here we have one case where there are no final marks on R. So remember F from the previous slide. So if there are no final marks from R, we shift everything in R and then we shift everything in S. And there is no concern of any marks falling over. Like we cannot have some marks which we discarded from R and we forgot to carry over to S. And this is the possibility that arises if there were final marks in R, because when we have these final marks in R, after the shift, they are supposed to become initial marks in S. So if this is the case, then we shift everything in S and we also add additional marks to the initial positions in S. So to do this, we check if we have any final marks in R. And the other thing with star is similar. So if there are no final marks under the star, then we are fine. If there is some final mark, then we could carry over this mark and pretend that it's an initial mark for the next configuration of the automaton. So if this is the case, then we call the initialize function again. Okay, the next part is what I call filter. And so when I have this kind of configuration and I say filter B, I get rid of the mark on A because A does not match B. And this one is quite simple to implement. So with all these tools that we have, we can do regular expression matching as follows. So R is the regular expressions that's originally given to us. And if I want to know if the empty word is in the string, is in the language, then I use this function new, which we saw before. And if the so we could stop here if we want. Otherwise, what we do is we initialize R to R prime using I, and I puts marks on the initial positions, and A naught is the first character of the input. We delete the delete every mark which is not which does not match A naught, and then we check if any of the final positions are marked. If this is the case, then A naught as a word is a part of the language of R. And then for the next thing, we shift all the tokens, and then we filter. We filter with respect to A1, getting rid of all the marks which do not fall on A1, and this, and then now if we see if there where the final marks are, we know where A naught A1 are. And similarly, we can keep shifting and then filtering to figure out if this current prefix is in the language. So the next question is how should we understand the semantics of these objects? Of course, these are like NFAs, but we don't want to define NFAs because we already did that in part 1, and hopefully we can have something cleaner for this part. So the idea here is that when I have a mark on Q, I would think of it as the future of Q. And by this, I mean, I will think of this as all those words which could be accepted if I was starting from that particular state. So we can make this formal as follows. So if we have a mark, we just use this letter. Union is simple, but notice concat. So for concat, we take the marked semantics for R, and then we have this. So this says that look at all the words that start from marked states in R, and then look at all the words that are start from marked states in S, and star is similar. So what do I mean by the notation strip S? So strip of the marked regular expression is just a normal regular expression with all the marks removed, as you would expect. So I have some examples here which will hopefully make this definition less mysterious. So here the semantics of this is just the empty set, because there are no marks here. So in the NFA that this represents, that NFA does not contain any futures because you couldn't begin your runs from anywhere. So here, this represents the string BB. Like, this represents the language containing just the string BB, because the idea is that you start from this mark and you are allowed to finish. So you get BB. If you had two of these, you get this, because either you start from this B and then you just get a single B, or you start from here and you finish and then you get BB. If you had this is your semantics, because you start from A, so you have to have an A, and then you repeat the whole thing. So I hope these examples illustrate this definition. So now, with the help of this this object, we can define we can make precise what the functions if and I and shift are actually supposed to mean. So now we can articulate them quite precisely. So this one we have already seen. This predicate is asking if the empty string is in the language of the regular expression. So this does not depend on marks at all. Here, this function if, which we said that it looks at whether something is in the final positions of the automaton. Using this object, we can describe this as follows. It is asking whether there is a word accepted by the marked expression of length 1. And indeed, you can see that this is the interpretation, because if we did have such a word, that would be in the semantics, because the semantics contains exactly words starting from the marked positions. This adds certain marks to the expression at hand, and by doing so, the additional words that we add to the language of diagonal semantic bracket it's basically the language these are the words that are originally inhabitants of R, except for the empty word. And shift is like computing a derivative, except that it computes this derivative on this diagonal semantic bracket. And filter simply removes all the words in semantic bracket R which do not start with A. And finally, if we remember this diagram from the previous slide, we are creating these expressions are not R1, R2, etc. And what do these expressions, what is the semantics of each of these expressions? They stand for all words of the all words of the following shape, which start with AI plus 1, and this and the prefix of this word matches the word that is given so far. So if we have these characteristic lemmas, then we are able to prove that indeed each of these questions answer whether each of these prefixes are matched by the regular expression. So coming back to efficiency, we need to make some small adjustments to this data structure. So I recall that the definitions of iota and shift, they utilize new and if. And new and if, they might look into the whole data structure, which might take linear time. So if if iota and shift compute them repeatedly, then they might take quadratic time, and we do not want this. So the solution is to instead of having to compute them again and again, we will add this information to the data structure. And this is a relatively easy trick. So this is what we had originally in the previous slides. So instead of this, we will have this kind of data structure where we will have additional fields which will have these booleans saying whether, so this boolean corresponds to new and this boolean corresponds to if. And if we need to look into if we need the values of new or if, we just compute them once and later we just project out these values. So to summarize efficiency, we have marked regular expressions of the same size as the original expression. And computation of new and if, when we compute them for the first time, we might take linear time to construct the whole expression, but subsequent invocations, they take constant time. And these computation of initialization, shift, and filter, they can also be done in linear time now with this trick. This means that just like the Thompson NFAs, we actually do a linear amount of work per input character. So now we can wrap up this section as well. Here, I think we have a relatively more elegant mathematical object here, and efficiency is still pretty good. And we have also a functional algorithm, and proofs are much more reasonable now. So let us summarize by just recollecting the pros and cons of each of these techniques one more time. So with Thompson NFAs, we have a very classic algorithm which can be implemented very efficiently. But the cons of this is that we have to reason about paths and we have to reason about graph search, which can be quite difficult to reason about in a proof assistant. With derivatives, we have very elegant mathematical objects, and the proofs are simple as long as we understand what derivatives are. And the concept here is quite extensible because people, as we saw, have taken this concept into various problems related to regular expressions. The difficulty is keeping the derivative size small. And with marked regular expressions, we saw that this is somewhat of a middle ground. And we had the semantics of these objects were perhaps somewhat non-obvious, but we still got back linear time matching and some purely functional algorithms. So if you want, you can look into one way of formalizing marked regular expressions over here. And if you want more details, you can read some chapters of my thesis. So thank you very much for your attention.